So good afternoon, everyone. This is our sixth online lecture for nuclear reactor kinetics and control. Before we start today's lecture, let me just briefly talk about some opinions from the students related to this online lecture. So, some students suggested that they actually prefer or they wanted to have a chance to see, instead of these real-time lectures, they would like to have another chance to see and to see this lecture in other times, so in the form of a recorded lecture. So maybe this is something, but one thing that I would like to emphasize is that the reason I decided to give this real-time online lecture is that at least during these 3 hours, you need to be focused on this lecture, and you should not be distracted by other things. So, and that is a way of increasing your efficiency in studying some topic. So, I have that intention for these real-time lectures, but mm, so so I hope the students also understand that. But if you think you also want some time to review what you learned during the real-time lectures, so for the purpose of providing such a review chance, I would like to reserve some time, not a long time, but a small time period that you will have some chance to also see the lectures, kind of see the recorded version of this lecture. But as I emphasize again, it is only for making up those topics, making up mm, what you want to learn, making up what you want to learn. Mm, so the intention is that it's not intended for you to give a chance to uh, a kind of chance that you will see all the lectures, and then you that means you don't need to attend the kind of real-time lectures. So my point is that I'm going to decide and assign a short period of time, like one day, and I will give you a chance to see the recorded version of these lectures, so that uh, during that time, if you first need to be prepared to utilize that chance. So that is because you cannot see all the lectures during just one day. So you need to have a specific purpose for seeing the recorded version of these lectures. Related to the midterm exam, it seems that students mm, do not want to take lectures, do not want to take exam, do not take midterm exam. So some students raised this opinion that they hope that midterm exam is substituted with some homeworks, and then raise the provide more importance on the final exam. Well, I will think about that, but of course, that does not necessarily mean that you don't need to study at this time point, and there is nothing you should do during the midterm exam time. I'm going to provide you some kind of homeworks, and that will be that homeworks will be the basis for your evaluation, for the evaluation of your grades. So I will think about substituting the midterm exam with some homework problems, and then that the result of homeworks will be the basis for your grades. And of course, related to the offline lectures, I deeply agree the opinion that this offline lecture is necessary. So we are going to gradually, of course, the university management gradually monitors whether we resume or whether we start the offline lecture after midterm exam. So these were the kind of my answers to your opinions about the online lectures. So as always, if you have any questions, please leave it. Raise your questions through the chatting window, or you may leave questions in our e-class board, or you can send me an email if and of course you may select any convenient way of raising your question. So where are we? So we started from chapter 5 of our textbook, and then after finishing chapter 5 we also studied the chapter section 7.6 in 7.6 in our textbook. It's page 186. Okay, let me reload our textbook. Number 86. So it was about, we studied about control poisons last time, and we studied how reactivity worth is estimated after when we insert control laws, and we learned two different cases. The first one is when we only insert a single control load, and and after that we learned the case of inserting the control load bank. And in this case, basically, when the assumption that we utilized for inserting control load bank is that the whole area or the whole volume, in fact the whole area, will be affected by the insertion of a control load bank. And so of course, if the control load bank is inserted to x amount of depth, then this whole graded volume will be affected by that inserted control load bank. And we derive those equations, and this equation 7.99 and 7.100, depending on depending on whether alpha is bigger than beta, or beta is bigger than alpha, we have these equations, and then this will determine the multiplication factor k after the insertion of control load bank, and because we have the change the multiplication factor, we are able to determine the reactivity. That is, in this case, if we inserted control load bank, then we are able to estimate, or we are able to calculate the inserted negative reactivity, by the insertion of control load bank. And here we also talked about two different cases. The first one is the tightly coupled reactor. That is the case when H over M, that is the ratio between the height of the reactor to the migration length. Of course, the migration length will be determined by the properties of the material. So, or in other words, the composition of the reactor, the enrichment of the reactor, and the diffusion coefficient of the moderator, and so on. So by comparing the ratio between the height of the reactor and the migration length, and also one more thing that I would like to add is that in this case, it is assumed that the radius of the first we think about a cylinder-shaped reactor, and it is also assumed that the diameter equals the height of the reactor. So if the height of reactor is determined, that means the diameter of the reactor is also determined in this case. And in that specific shape of reactor, if this ratio, height to migration length, is around 10, and this 10 is considered as a small value, and that is the case of a tightly coupled reactor. And when this ratio approaches 50, it is called as loosely coupled core, or loosely coupled reactor. So the difference that we can see in here is that in case of when we inserted the control load bank into the reactor, in case of tightly coupled reactor, so even though we inserted deeper and deeper, but the overall shape of the reactor, overall shape of a neutron flux in the axial direction. So this the point where this G over H equals 1 is the top of the reactor, and 0 indicates the bottom of the reactor. So I hope it is I hope it would be helpful. So if we rotate this to the counterclockwise, or counterclockwise. So this would be the shape of neutron flux in axial direction. And even though we inserted a quarter, when the control loads are inserted, let me use this. So even though when we inserted the control load bank to the half of the reactor, or in this case almost the half, first the quarter of the reactor, second almost the half of the reactor, and in the third case it is also almost inserted to 3/4 of the reactor. So in these three cases, let me move in these three cases, but the overall shape of neutron flux do not significantly change. So that is why it is called as tightly coupled core. Okay, tightly coupled core. So on the other hand, let's move to the second case. Okay. So in our second case, so once again, I'm going to rotate this to counterclockwise. So let me move these three different cases. So let's see. This is the case when we inserted a quarter from the top, a quarter of when we inserted the control rod bank to the depths of just a quarter of the overall height. And the second case would be when we inserted the reactor at control rod bank to the half of the height. And the third one about 3/4 of the height of the reactor. And you can see that, so if you see this figure, you may understand why this is called as loosely coupled core. So compared to the first case, and so this is the case when height over migration length is around 10, and this is the case when height to migration length is around 50. So you can see that it is much loosely coupled. So the neutron flux in the upper part is different from the neutron flux in the lower part of the reactor. So, whether a reactor core is tightly coupled or loosely coupled is determined by this ratio of height to migration length. So these were what we studied last time, and I also ask all of you to, or I'd like to see whether any student is able to draw these figures based on the mathematical analysis results provided in our textbook. So if you utilize all these mathematical descriptions, if you utilize these descriptions, and if you understand these and actually implement this, then you will be able to draw all these figures. So let's see who is going to be successfully, who is going to be accomplish or finish this challenging problem. So we just finished the chapter or section 7.6 in our textbook, and from today we are going to talk about chapter 8, energy transport. So energy transport. So so if we read the textbook, so we are currently or the subject that we, or the title of this course is nuclear reactor kinetics and control. And then the question that may be raised is, why do we study energy transport? So the reason we study energy transport is that is that so these preceding chapters concentrate on time and space distribution of neutrons and so on. And if the reactor power is very low, these equations will be valid. So that is why when we study chapter 5, at the end of the chapter, it was mentioned that those theories that were described in chapter 5 were zero power kinetics. And that means that those theories will be available to only to the case when the reactor power is very low. If so, in case of a very high power, we are going to see two important limitations. And of course, the purpose of a nuclear reactor is to produce energy and utilize and produce the energy and then transport the energy so that that energy can be converted to other forms of energy like mechanical and then electrical energy. So utilize such energy, we need to to utilize such energy, the first limitation is that the energy must be transported. The energy must be transported. That is one consideration, one energy related consideration that we need to think about in studying or in designing a nuclear reactor core. And another consideration is that the second one is that, well, as temperature rise, density will change. Of course, the density of the moderator or density of the nuclear fuel will gradually decrease as we increase the temperature, because we are going to have the same mass, but as the temperature increases, the volume will increase. That means the density will gradually decrease. And if density changes, then atomic density will be affected. If atomic density is affected, then macroscopic cross sections will be affected. So there are this type of temperature related phenomena, or what we would like to say, what we would like to call temperature related reactivity feedback. So the reactivity will be affected by the temperature. As temperature increase, then the reactivity will be affected. So let me write this down. So there are two important limitations. The first one is that energy must be transported. And second second important consideration is that we have temperature related reactivity feedback. So let's move on to, so basically this chapter examines energy transport from the reactor core, and And then we are going to see what thermal limits will be imposed. And after that, in chapter 9, we are going to examine reactivity feedback effect. So basically in chapter 8, we are going to focus on the transport of energy. And the thermal limits. And then, of course, we are going to have some also learn about how the disturbances in temperature will affect the reactivity. So anyway, let's first talk about core power distribution. So that is a section 8.2, core power distribution. So when there is something that we need to think about when we design reactor core design. So let us first define a new factor called power peaking factor. So power peaking factor here is in fact the ratio of a maximum to average power density. So that is power peaking factor is defined as F subscript Q, and that is defined as the ratio between the maximum so if we write P and triple prime, so it means that it is a density it is a kind of, so we once again, so power to triple primes, that means it is kind of a power density divided by, so that amount of power divided by volume. Double prime usually indicate some quantity, in this case power divided by two-dimensional quantity like area. So that in that case it is going to be like surface power density or surface heat rate. So just one prime, single prime will usually indicate the quantity power divided by one-dimensional quantity, one-dimensional length. Like, so in that case it is going to be linear density or linear power rate. So this is going to be the power density, the power divided by volume, and it is and this is going to be the maximum value of this. So in a reactor, we are going to, in a reactor, power density will vary depending on the location of the reactor, and we are going to take the maximum value of that divided by power, the overall power density. So this is going to be the average power density. So in this case, the denominator will be given as the power that we expect from a reactor divided by the volume of the reactor. So this is going to be the overall average of the power density. So if we have this, then the equation that we are going to have, of course we can write one more line that will move this volume to the numerator. So this is going to be same with moving V to here. So it is going to be simply P. So if the equation is like this, then of course power will be given as maximum power density divided by power peaking factor multiplied with the volume. So if you look at this equation, so what this equation implies is that P is usually determined. So when we design a reactor core, the overall power that the reactor core needs to produce is usually determined. So for example, we would like to design like 4,000 megawatt thermal reactor. So P is or some value that is already determined. So, and after that, well, the volume. So as usually the volume is the volume of the reactor core. That is also the size of reactor. So if the volume is increased, then we need more material to produce that reactor. So that means if we increase the volume, then we also, and in that case, the price of a reactor will gradually increase. And so it is, so usually when a reactor is designed, then we would like to minimize volume as much as possible. So if P is already determined value, if P is a kind of value that is already fixed, and if we increase volume, if we would like to minimize the volume, then that means we need to maximize this ratio. And in maximizing this ratio, this maximum power density is usually determined, or there are some design limitations or physical limitations are imposed. That is, some material will not be able to withstand or heat, because heat should be transported. Then the amount of heat that needs to be transported will be a limitation that will be imposed in, and that kind of limit will determine the maximum power density. So if you would like to maximize this factor, then we should minimize this power peaking factor. So therefore maximize this ratio in fact means minimize this power peaking factor. So how can you do that? Well, this is because we in case of a uniform reactor, in the radial direction, Of course, we are going to also learn about this as an example, but in case of radial direction, in case of a uniform reactor, then the shape of the reactor core will follow a Bessel function. Let's see whether we can find that curve. So here, page 172. So in the radial direction, this Bessel function so at the center of the reactor core, and then reactor power gradually decreases. And so we are able to calculate the maximum to average power density in this case. So then if we would like to minimize that power peaking factor in the radial direction, then we need to manage the distribution of nuclear fuel. So we may change the enrichment like that, so that the shape of neutron flux becomes more flattened. So let's see whether, so because of that purpose, maybe I hope in, let's see, page 88. So this is the example of reactor core, and different color indicate different enrichment, and this type of arranging different enrichments in a single reactor core instead of utilizing a uniform enrichment. The reason is because we would like to flatten the neutron flux shape as much as possible. So let's go back to our chapter 8 in page 200. Another example that so we just talked about this equation 8.3. We would like to minimize FQ, and this table 8.1 gives us some data about some parameters that we talked about. So this is table 8.1. So it provides us some data about 3,000 megawatt thermal power reactor. So with the 3,000, that means 3 gigawatt thermal. In such cases, this kind of reactor may produce about 1 gigawatt of electricity. And in Korea, in our country, the OPR 1000 will be almost equivalent. Will produce this amount of thermal power. So in such case, pressurized water reactor, the power density megawatt per cubic centimeter, and of course we are going to also talk about this average linear heat rate. So this linear heat rate, I mean the maximum linear heat rate, will provide some limits to the amount of power that can be generated by per unit volume. So this maximum linear heat rate will limit the maximum power density, and the average, usually typical volume of reactor core, and also we can see the ratio of height to migration length. So if these data are around 43, 55, 40, and in this case is the reactor. So in what we learned in section 7.6, from what we learned in section 7.6, these types of reactor belongs to the loosely coupled reactor. Here the second one. So with that value, these PWRs or BWRs usually belong to loosely coupled core. And the number of field pins and non-leakage probability, these data are also given for 6 different types of reactor core. So PWR, BWR, and CANDU reactor, high temperature gas cooled reactor, sodium fast reactor. So in this case, sodium cooled fast reactor and gas cooled fast reactor. So let's move back to our textbook. So this table 8.1 provides us some typical data that we can utilize in understanding what is provided in this chapter. So let's just think about finite cylindrical core. So once again, let me show you this figure. So in fact, I drew this figure myself, and we are going to think about a cylindrical reactor core. So in cylindrical reactor core, so back to our textbook. Let's think about how we are able to calculate the average power density. So section 8.2. So finite cylindrical core, and let's calculate the average power density. The average value of this. So this is the average. To calculate the average value of power density, then what we should do is to calculate the overall power divided by the volume. So to calculate the power, we should integrate. So if, of course, depending on the geometry of the vector, geometry of the vector core, the power density as a function of its location can be calculated. So R vector, indicates the location of the reactor, at the location of interest. Divided by, multiplied with small volume dV. So this equation applies to any reactor core. In case of a cylindrical reactor core, then in case of a cylindrical reactor core, oh, let me rewrite this. So let's first think about the volume. In case of a cylindrical reactor core, the volume will be provided as pi and radius squared multiplied with the height of the reactor. So this would be the volume of the reactor. And in fact, of course, it should be the triple integral and power density. So power density. So P prime R vector. Let me slightly correct this. So this is now changed power density at the point in case of when we use the cylindrical coordinate system, then the location will be given as R, and let's use theta and Z in axial direction. What about dV? dV will become R dr d theta. More clearly, R dr d theta and dz. So this would be the dV in case of cylindrical coordinate system. Integration should be performed in case of R from 0 to R. In case of theta from 0 to 2 pi. And in case of Z, let's call it as integration from minus the half of the height, h divided by 2 plus h divided by 2. So if we do not have any dependency on theta direction, azimuthal direction, then this P prime, the power density, will become the constant with respect to theta. So in that case, this can be simply become, so it is not going to be dependent on theta, but just 2 pi as a result of integration will remain here. So this is the equation when this power density do not depend on theta. And after that, we are going to use the relation that this power density or power at any point is we are going to divide that power peaking factor in radial direction and axial direction. So that means the power at the point of some r from the center and g from of course g from the center of the reactor core, the average value, so this the power density at a specific point is given as the average power density multiplied with some another function called another function for the change of reactor power in radial direction, and also the change of reactor power in axial direction. So if we assume that power density at a specific point is given like this, then we may rewrite this equation as, so instead of power density at a specific point, power density at a specific point is given with this equation. So what can you do with this? So this average power will be just constant with respect to the radial direction, and I'm sorry, I should also erase this theta here because we do not have any dependency, and 2 pi is just the result of this integration. So in the radial direction, we are going to take this average value out of the integral, out from the integral. So we are going to take this out, and we are going to cancel the pi here and also the pi in the numerator. Then and also these two, this is going to be g and fg will not be dependent. I mean, this is just a function of only axial direction, z. So this will not be dependent on the radial direction. So this can be taken out. So what we are going to have is, this is just 1, and so after calculating this, and then we also calculate the second part. And we are going to move r squared h. So we are going to kind of distribute this. So r squared will be placed here. So 1 over r squared well, 1 over r squared, and also we are going to insert 1 over h here, 1 over h here. So then in that case it can be just average power density, and because 2 is just constant, we may take this out to here. So what does this mean? So average power density, so also we have another average power density here. So this means that this integration should become 1. So that means WHERA. So this integration should be 1, and also this integration also should be 1. So these relations are given in equations 8.9 and 10. And we are going to define, so previously, so power peaking factors, so we will be able to so we are going to define two power peaking factors. So capital R subscript R will be the power peaking factor in radial direction. So it can be called as radial power, radial peaking factor. And also we are able to think about the radial peaking factor in axial direction. So of course this would be the maximum value of FR. This would be the maximum value of FR. Also, similarly, FG, axial peaking factor, will be the maximum value of FC here. And also we are going to, so these two will be defined theoretically, and also we will be able to define another one called local peaking factor, denoted as F subscript L. So this local peaking factor is for considering all other types of elements like fuel element, manufacturing tolerance, and in local control, instrumentation perturbations, and so on. So now the question would be, how can we determine these radial and axial peaking factors? So this figure 8.1 shows us radial power distributions. So in fact, this one shows us this function FR and R, the FR of function of R. And previously it was mentioned that making this distribution as uniform as possible is one of the most important considerations in designing reactor core. So what we can see is that instead of a uniform distribution, if we divide the sections into two, then we are going to kind of reduce the radial peaking factor. So we are going to reduce the ratio between the maximum power to average power in this case. So that means non-uniform distribution will be more preferable in minimizing this radial peaking factor, and that is why in chapter 4 we could see that the distribution of different enrichments when we design a reactor core. So anyway, in this example, at least in case of uniform cylindrical core, we are able to actually calculate the value of actual radial peaking factor and axial peaking factor. So the function in the radial direction, it follows a Bessel function, and in axial direction, it follows the cosine function. So if we utilize, so we derived equation 8.9. So integration from 0 to r, of the distribution in radial direction should be 1. So with this, we are able to determine CR, and also in a similar way, we are able to determine CZ. And the result is that this function of FR is given as 2.32 and Bessel function. In case of axial direction, we are going to have 1.57 cosine. I hope whether you are able to guess where this number of 1.57 come from. So to determine, in case of this, so in fact this 1.57 come from the half of pi, so pi divided by 2. And in case of the first one, so if we utilize our MATLAB, then this is CR. So in our previous case, so CR and this integration should become 1. That means CR should be given as 1 divided by this integration. So this integral of 2 divided by r squared, and integration over Bessel function and 2.405 r divided by r, and we multiply r, and then integrate this, numerically integrate this from 0 to r. And the result is the CR is given as 2.365, and this is half of pi, and if we multiply the 2, we get 3.6387. So these numbers are given in equations 8.20, 8.21, and 8.22. So the point is that, so from these properties, that this FR function should satisfy, and this FG function should satisfy. And in case of uniform cylinder core, we are able to calculate FR as, let's see, FR was this 2.3165. FG is in fact given as half of pi. And FQ is given as the product of FR and FG. So I hope you all of you also try yourself how these numbers came from, and actually draw the shape of a neutron flux, so that you can understand why minimizing this radial picking factor and the radial picking factor is important in extracting maximum power from the volume of the reactor that is already fixed. So we just finished section 8.2, and well, this already 4:10, so why don't we, even though it is a little bit early, but why don't we stop at this point and then take a short like 15-minute break, and then continue to learn about heat transport in section 8.3. So we are going to restart at 4:25. And I also, as always, I also would like to ask all of you to leave your name to check your attendance. Okay, let's start the second half of today's lecture. So we are going to talk about heat transport in section 8.3. Heat transport. So we are going to talk about the steady state heat transfer. So we are going to use relatively simple, we consider a relatively simple model, and a very simple case. So the target, the reactor that we are going to consider is a cylindrical reactor. So let me show you this figure one more time. So basically this is the case that we are considering. Okay, let's try to move this figure to our note. So 8.3 is about heat transport. And I hope you to remember currently thinking about a vector core in this shape. So the first thing that we are going to think about is linear heat rate. That is denoted as Q prime. So Q prime as a function of R and Z. So this is the linear heat rate. So this is a single ferrite, and maybe at any specific point R and Z, then we are going to think about the linear heat rate at that specific point. And that's equation that is also included. I mean, in our textbook, this linear heat rate is placed in many different places, and we are going to first focus on this linear heat rate. So another figure that we need to take is this. So this is the figure that we see this shear load from the top. And of course, in this case, the radius of the shear rod would be A. And if the same amount of, so if the heat is produced inside of the shear rod, then that heat need to be transported through the surface of the shear rod. So when we think about the Q prime surface heat rate, surface heat flux, so if we need to think about surface heat flux, then the relation between linear heat rate and surface heat flux would be 2 pi A. 2 pi A would be, of course, so 2 pi A multiplied with the height will be the amount of the surface area of the shear rod. And so if we see this figure, then in this case, of course, if we see all the height in the reactor, so all the height of the shear rod, then the surface, the heat generated inside of the shear rod should be transported through the surface whose area is 2 pi A multiplied with the height. So just like that, for any specific point, we are going to multiply dH instead of, so it is like Q prime, I'm sorry, Q prime, so the amount of heat generated is that the linear heat rate multiplied with dH. So we are going to take a very small height here that will be same with 2 pi A multiplied with dH, H, and then this would be the surface heat flux. So we simply divide the dH in both sides. So linear heat rate is given as 2 pi a multiplied with the surface heat flux. Then, of course, in equation 8.23 in our textbook, if we divide 2 pi a, so if we divide this linear heat rate with 2 pi a, then we are going to get the surface heat flux. So this linear heat rate is also should be same with, so if we think about also a very small height dh, so let me just once again, maybe it is better for you to put dh here. This dh will help you understand the meaning or the problem that we are currently solving. So in the same way, if we want to calculate the total amount of heat that is escaping, or if we first we consider the total amount of heat that is actually escaping or escaping through this surface is the second term, and this would be the amount of heat generated for very small height dh at a specific point of R and Z. And that amount of heat should be transported through, so if we see the reactor that consists of many channels, then of course the total the P triple prime would be P triple prime would be the heat, kind of average heat generated at this specific point. So the average power density for this point would be this amount of power density multiplied with this volume, multiplied with the area of the cell multiplied with the dH. So it is like multiplied with a cell, that is a cell is the area of a single cell. So the total power generated inside of so if we calculate the average power density for this point, then we, of course, the heat is only generated inside of the fuel rod. But if we calculate this average, then this average multiplied with the area also multiplied with the dH would be the volume of interest, and this will be also same with the amount of heat generated from the fuel rod multiplied with this dH, the very small height here. And also, so if we think about this relation, then the power density at a specific point power density at a specific point was considered to be same. So average multiplied with this fr and fg function. So we are going to just use this relation. So instead of power density at a specific point, we are going to replace this with this equation multiplied with a cell and very small height, dh. And what about this? The average power density. Average power density will be given as the total power divided by the volume. The total power that is produced from the reactor divided by the volume of the reactor. And then what about the relation between the volume and a cell? So if we assume where the total volume, if total volume is given as, so let's assume that this all volume is completely filled with n cells. So there are in total n number of this kind of cell. And in that case, the total volume will be equivalent to first, so let's first calculate the volume of a single cell. So the area of a single cell will be a cell multiplied with, to calculate the volume, we need to calculate the height of this cell. And the height will be given as h. And let's assume that this volume, the reactor volume, is completely filled with n cells. So if you see this relation, then volume is given as nh multiplied with a cell. So this is actually nh and multiplied with a cell. So in other words, if we rewrite this, it becomes like this. And this a cell cancels each other. So a cell in the numerator and denominator cancels each other. And this is the kind of result that we are going to get. So with this in mind, maybe we may review what is written in our textbook. So this surface heat flux is given as 1 over 2 pi a multiplied with q prime, and this q prime also equals the power density multiplied with a cell. So if we multiply dh to both left and right hand side, then that is the equation that we consider here. And this q prime is also given. So if we rewrite the power density at this specific point with the average power density multiplied with FR and FG, the functions for peaking factor, and then we are going to simply the power is given, average power density is now rewritten as power divided by volume. And with consideration of the relation between the volume and the area of a single cell, a cell, then in this case we are going to have, because the volume is given as NH a cell, so only 1 over NH remains here. So here we have the relation between linear heat rate and the power, and these functions for peaking factor, and N indicate the number of cells, and H is the height of the reactor. So with this in mind, also we are going to talk about some temperatures. So related to the linear heat rate and all other relations, so with these figures in mind, and one more figure that I would like to add is this. So let's assume that the reactor is completely filled with all these cells. So this reactor has n number of these, actually what we call as field channels. So in this case it is called as a single cell. So let's assume that the reactor consists of n number of field cells, and I hope that all of you try to derive all these relations yourself to completely understand all these relations provided in this textbook. So next we are going to talk about some relations about temperatures. So this first, this linear heat rate. So usually linear heat rate. So our basic understanding is that if the temperature difference is high, then the higher the temperature difference is, and the bigger this linear heat rate will be. That means if there are more, so here we have a shear region and coolant region, and if there are more difference in the temperatures, so if the temperature between difference between the fuel and coolant is high, then more heat will be transported. So that also means that the amount of heat transported also give us some information about the temperature of the fuel. So anyway, the linear heat rate will be given as temperature difference multiply, actually it can be considered that temperature difference. So in this case, temperature of a fuel element at this specific point, and the temperature difference between the fuel element and coolant. And we are going to multiply some constant here. And the constant can be also expressed with some resistance. So fuel element prime. So just like current, the current is given as the temperature in potential, the difference in potential. So the difference in voltages divided by its resistance. The heat rate is given as the temperature difference divided by its resistance, some thermal resistance. And previously it was given, so if we also ignore dH, then this linear heat rate will be given like this. So if we move 1 over NH to the denominator of the left hand side, so we just leave P here. However, we would like to move 1 over NH to the denominator of the left hand side. So it is going to be changed like this. So this is the relation. So here we have so the first line was equation 8.29, and then this is going to be, this is the equation 8.30. And of course, from if we also once again we are going to move, this parameter to the right hand side. So of course it does not have any denominator, it becomes like this. And then we are going to integrate over all volume. So we have R and G, and we are going to integrate this over all volume. So first we are going to place a parenthesis and then integrate over all volume. That will be same with integrate over all volume. And divided these with divide this with 1 over V. Divide this with 1 over V. So we would like to calculate the average value of fuel temperature and also average value of coolant. So with this, this is, in fact, previously it was just the temperature of a single fuel element. If we integrate over all the volume of the reactor, now it should become, instead of a fuel element, it should become the average temperature of the fuel. Average temperature of the fuel. And the second term will be the average temperature of coolant. Or let me use this. So average temperature of coolant is given. Let's think about the right hand side. So power, if we take P, that is going to be we have a total power here, and so this is thermal resistance for a single fuel element or a single fuel cell, and if this is divided by NH, that is going to be RF. So I should add one more thing here. So this denominator is defined as R. That is so RF. And so this RF is the thermal resistance that can be. So we may replace this with RF, and we have a P here, and RF will be also a constant. So this is going to be, because RF is a constant, it can be taken out from the integral. And for the whole volume, integration over FR and FG is going to be simply 1. So for the volume, maybe this full integration over all volume can become a double integral for R and Z. And then so what I'm saying is that we are going to have R and P, and instead of this the volume, it can be now rewritten as pi R squared NH, and instead of this, the integral now becomes a double integral by assuming that we do not have any dependency on zeta, a sinusoidal direction. And FRFG multiplied with, so because we do not have any dependency on a sinusoidal direction, the integration over that zeta direction, a sinusoidal direction, will result in 2 pi from R equals 0 to H, from R equals 0 to R, zeta, in case of actual direction, it is H over 2. So and of course H, we are going to divide this with pi R squared, and H And just like what we did previously, pi cancels each other, and 2 over r squared and FR dr will become 1. So here I would like to I hope you remember all these relations. This integration should be 1, and also this integration should be 1. So that means all this integration, in other words, this should become 1. So the right hand side would be simply RF and P. RF would be the thermal resistance when we consider the whole volume, and P is the power produced from the reactor. And next, we are going to consider a coolant heat balance for a lattice cell. So that means, so from here maybe it's better to see this figure. So for a single lattice cell, so the temperature, inlet temperature will be uniform. That means the coolant temperature that is entering from the bottom do not have any dependency on R and G. In fact, it does not depend on R. So at every point, at every lattice cells, the coolant enters with temperature Ti. It is not a function of R. But because we have different distributions or power distributions in radial direction, so the outlet coolant temperature will depend on the position or location of the fuel rod. So the outlet coolant temperature will be dependent on its position. So T outlet temperature depends on this value R, the distance from the center, the distance of the fuel rod from the center. So, and the coolant with the temperature Ti enters here, and it is going to receive heat, and as it receives heat, its temperature gradually increases, and then it exits the reactor with the temperature T out, TO, and the amount of so when we think about that heat balance, then the amount of heat generated from the fuel rod will be same with the amount of heat that is carried by the coolant, and that amount of heat will contribute to increase the temperature of the coolant. So with that in mind, so the amount of heat provided by the fuel rod will be, so this is the amount of heat generated per unit length linear heat rate. If we multiply dg, then it is going to be the amount of heat generated from the fuel rod between G and G plus dg. And to calculate total amount of heat generated, we need to integrate this from minus h over 2 to h over 2. So this is going to be the total amount of heat. So in other words, so this equation gives us total amount of heat generated. Total amount of heat generated from the fuel rod. And that amount of heat should contribute to increase the temperature of the coolant. So that can be calculated as, so to calculate that, of course, we need specific heat of the coolant multiplied with, in fact, C. This is what we call as mass flow rate. So the amount of coolant that is flowing per unit second. So because the left hand side is heat rate, the amount of heat, heat. So if you remember the relation of heat, so if the equation is applied to the total amount of heat, that the heat equals mass multiplied with specific heat multiplied with temperature difference, delta T. And because the left hand side is the equation for heat rate, so the heat produced per unit time, so the right hand side becomes, instead of mass, it becomes the amount of mass that is flowing per unit time. So now we have WCH, that is the amount of coolant mass that is flowing through a single channel or single lattice cell of a reactor. So WCH is going to be the amount of mass that is flowing through this single lattice cell per unit time. So mass flow rate multiplied with specific heat multiplied with temperature difference. So in this case, the temperature difference will be the outlet temperature at the location of R minus inlet temperature. And I told you that we assume uniform inlet temperature. So maybe to avoid confusion, let me use bracket instead of a parenthesis. So with this, we are able to calculate the outlet temperature. So the outlet temperature is given as, so let me rewrite this one. So the final object is to find the outlet temperature. So for that purpose, the mass flow rate and specific heat will move to the left hand side, and then we are going to add Ti. So it should become plus Ti. And this becomes the outlet temperature. And that's equation 8.36. Oh, I'm sorry. That's equation that becomes equation 8.34. There's one thing that we also need to add is that, so what about this q prime? Q prime is given, so q prime is given, previously it was given as so let me take the relation, not here. So here q prime was given as average power density multiplied with Fr and Fg, and average power density was given as P divided by V, Tp, the power divided by the volume of the reactor, and after the area of the cell is cancelled out in both numerator and denominator, we have this relation. So that means q prime in this equation also, q prime can be given with this relation. And the power, number of lattice cells, and height, these are all constant with respect to dg, with respect to the parameter for axial direction. And in fact, Fr is also only function of r, so it is relevant to z, so this also can be taken out. And maybe we are going to just place h here. So instead of here, we are going to place h here. And I hope that you also remember what this integral will be, integral will become. This integral is simply 1. So if I take this bracket, this is simply 1. So the outlet temperature at a point that has distance r from the center will be given like this. It is also, of course, a function of r, and it also dependent on many other parameters such as power, number of lattice cells, and WCH is going to be the mass flow rate for a single lattice cell. So another thing that we can think about is if we move n to here, then P will be simply P here, or P can be placed here. So if we replace WCH is the mass flow rate for a single channel or a single lattice cell. And if we have n number of lattice cells, then this is going to be, so we are going to define W as m multiplied with WCH, that is the mass flow rate of a single fuel cell multiplied with the total number of lattice cells. So W is in fact the mass flow rate, total mass flow rate. So it is called as core mass flow rate. So by simply introducing W, this becomes W FR plus TI. So if we, to be consistent with what is written in our textbook, now this is equation 8.36. So once again, if we go back to our PPT file, so what we calculated is the temperature, the outlet temperature, and the outlet coolant temperature from distance r. And so outlet coolant temperature from the point which is let's say where which has the distance r from the center of the reactor core. So this is what we just calculated, the outlet coolant temperature at point R. So maybe let's go back to the figure. So maybe if we know the outlet coolant temperature at a specific point, then maybe we would like to calculate kind of average outlet temperature, average outlet coolant temperature. Of course, that can be also calculated by integrating this outlet temperature at a specific point. So, of course, that can be calculated as, if we integrate this, from so basically we should integrate this over the surface. That means we should do the double integral. But if we do not have any dependency on theta direction, on that azimuthal direction, then the integral will be RT0R and 2 pi R. So of course this 2 pi comes from the integration over theta from 0 to 2 pi. And then after that, if we divide this with the surface area of the reactor, that is going to be pi capital R squared, So if we do this integration, and of course the same integration should be applied to the right hand side. So I'm going to take this bracket here, and then integrate this. So basically we are going to apply the same thing to both left and right hand side, and then multiply with the 2 pi r dr. So if we actually calculate this, the left hand side will become the average outlet temperature, because this is the definition. In fact, this is the definition of average outlet coolant temperature is given so if we do the integration, then of course 2 pi r, and so we have just like the case. So WCP can be taken out, P can be taken out. It is going to have FR and RDR. R, the pi in both numerator and denominator will cancelled out. So the first term will be simply, this is the constant part. So these are the constant parts. And the integration over FR will become simply 1. In other words, if we take this out, then the remaining integration will be 1. So about this 2 Ti, it is a constant, so plus Ti is a constant, and what will remain is pi r 1 over pi r squared integration from 0 to r. Ti is taken out, and 2 pi r dr. Of course, integration 2 pi r dr will be pi r squared. That cancels. So both the pi r squared in both numerator and denominator will cancel out. So this will be what will be remaining to us. So of course it would be deriving this equation would be also easy if we think about this. Or pi, the power, that is the energy per unit time, is the same with respect to the temperature, the mass flow rate multiplied with the specific heat and the delta T. So delta T is the average outlet temperature minus inlet temperature. So in this case, so if you also see this equation, then this relation is quite straightforward. So what we know is that so if we know that this is the outlet temperature, so if we move to our figure, then maybe we now know that this is given like this. The outlet coolant temperature is given like this. And next, and of course we are able to calculate the average temperature. So the average temperature is also the average temperature will be also the average outlet temperature is also given with this relation. So the only difference is that we do not have FR. So next we are going to calculate average coolant temperature. So this is average outlet temperature, and this is going to be Ti is the uniform inlet temperature. So in that case, we will be able to let's go back and write the equation. So what about average coolant temperature? So the average coolant temperature will be denoted as Tc, so average Tc. That average temperature will be given as the half of average outlet temperature and inlet temperature. So because this is average outlet temperature, so we have first we have two TIs, that becomes Ti simply. So it is like half will be multiplied. So first these two TIs become 1 Ti out of this 1/2, and this 1/2 can be placed to here. So this is the equation for average coolant temperature. So of course this was calculated as the half of, or the average of, average outlet temperature and the inlet temperature. So if we know the coolant temperature, so previously we calculated this relation, the relation between average fuel temperature and average coolant temperature and the power of the reactor. So that means this average fuel temperature can be calculated with this equation, RFP plus average coolant temperature. And because the average coolant temperature is given, so first RFP plus average coolant temperature is given in this equation. So we may take P out. So from this parenthesis, we are going to take P out. So that is equation 8.41. So this is equation average coolant temperature is given in equation 8.40, and average field temperature is given in equation 8.41. And next, let's try to calculate maximum field temperature. So, as you can see, it seems that it is like we are calculating a lot of different quantities. So we are calculating many different quantities. But as you may also see that even though the number of quantities we are calculating is many, but in fact they are not quite the way we calculate these are basically some simple arithmetic operations like add, addition, subtraction, multiplication, and division, and then use a very simple integration relations. So even though there are many quantities to calculate, but if you try to derive these relations one by one, then I assume that that is not going to be very difficult, even though you derive these relations yourself by referring to our textbook. So next one would be maximum field temperature. Of course, in designing a reactor, past the maximum field temperature provides an important limiting condition. So we know the melting point of nuclear fuel. So for example, if we use uranium dioxide, then we know its melting point. And after providing some safety margins, and then we may provide some limit that field temperature should not exceed at any point in the reactor. So for that, in that sense, this maximum field temperature should be always smaller than the limit provided or the limit decided from the melting point of nuclear fuel. So how can we calculate the maximum field temperature? So to do that, maximum field temperature will be related to the linear heat rate. Let me rewrite this. So linear heat rate. So maybe it is related to maximum linear heat rate, because you may think that the point where we have the maximum field temperature is the point where we are going to have the maximum linear heat rate. So, or you may assume that this maximum linear heat rate can be obtained at the center of the reactor. So R equals 0 and G equals 0. So in other words, so I told you that we were so let's instead of copying the relation, so if we move, let's try to take the relation here. So previously this was the relation. In steady state, the linear relation between linear heat rate and the temperature of fuel element and coolant temperature. So at point 0.00, this should be 0 and 0, 0. So at the center of the reactor, we expect the maximum heat rate and also the maximum fuel temperature. So of course this would be also considered as the maximum fuel temperature. So I'm going to write it as TF max. To write this as TF max. Minus the maximum coolant temperature. So so how can you calculate this maximum coolant temperature? So you may assume from here it can be here what is expected is that this is average coolant temperature. So also it is same with the average coolant temperature at the half of the reactor height. So what I'm saying is that from here the coolant enters with the temperature Ti, and maybe why don't we take the relation here. So this is average coolant temperature. So this is average coolant temperature. And if the height of the reactor is h, then so what you can see is that the amount of heat that is received, I mean or let's put it in this way. So so when we want, so let's keep this in mind, and what would be the coolant temperature, average coolant temperature at this point? So so how should I write it? Tc over so let's write it in this way. So coolant temperature at any location R and Z, but where the Z equals 0. So that is at the halfway along the halfway along the halfway along the lattice cell. So in that case, in total, so if we may think about this concept, then we may take average value, average coolant temperature, we may have average okay. When Z equals 0, so let's consider this when the coolant, I'm sorry. So let's consider this outlet temperature, the average outlet temperature, as the average value when G equals H over 2. So that means coolant temperature when G equals H over 2, and this is the coolant temperature, average coolant temperature when G equals 0. Then what would it be? And to calculate that, you may think about this in this way. So okay, parenthesis minus Ti. So if we rearrange this relation, then P, you may see that P equals WCP and the average outlet temperature. So just like this. This is what we would like to calculate. And the average temperature, the average coolant temperature when G equals 0 minus inlet temperature multiplied with mass flow rate and specific heat will be same with, so in case of outlet temperature, it receives the whole power, all the power of P. But if in this case, when G equals 0, because the coolant only experienced the half of its way inside of the reactor, so the amount of power that those coolant receive will be almost only half of the total power. So it moved only half of its way, so it received only half of the total power. So if we use this relation, then we are able to calculate the average power, average coolant temperature when G equals 0. So this is going to be half 1 over 2 pi 1 over 2 pi, and 2 should be divided by WCP, and plus, instead of a minus Ti, it should be plus Ti. So this is kind of average temperature. So if we would like to also include the dependence on R, then, so if we would like to calculate this, the temperature at R, then we need to FR, you need to multiply FR dr. So well, it is somewhat difficult to explain. Anyway, so this should be the equation for this. So this relation, in fact, should be placed here. Well, so maybe next time, it is already 5:46, so maybe next time we should start from here, from this topic of a maximum field temperature, especially how to provide the coolant temperature at the center of the reactor. So maybe we are going to stop here, and we are going to see each other next Monday.